it's good. Alright, I'm just gonna turn this to you guys so you guys can see here. Because they fixed the light, but they haven't fixed this light bulb. So super dim. Super dim. Yes. Which color is it?
Uh,
Static. Static.
oh yeah.
Sunday, you have to solve all the bad stuff.
That's what I do.
This guy.
Yeah, that first one where it's like, what fraction, and like, I basically did did that equation that they give us, right? And when I canceled and put stuff in, I got 1,
Interesting.
and or like basically it was just the rotational, translational. Right.
What is this? A thin puck? Thin puck.
Why are you here? I
Why?
already did it.
Why? I said I'm the type of person who will leave everything right before deadline.
Oh.
So he's basically saying that he's basically.
But this is not right before the deadline. This
I
is 6 hours, 6.5 hours before the deadline.
I haven't initiated, so.
Ah, snap.
Oh,
So
see, it's not.
It's due today, but we just get 10% off if we do it tomorrow.
Yes. Yes.
You want
This is-
That's
100%.
cool. That's so cool.
No, you want 100%.
Ooh, yes. This is also very true. All right. Let me check this out.
But then again, the homework is probably only like
Uh-oh.
compared to other stuff, like the pre-lectures and all that.
3 lectures. This is 2/3. This is 2/3.
But how? Where's the 3 come from? There shouldn't even be a 3. Because this is a cylinder. Cylinder is 1/2 in MR. There's no other, like, where would you get the 3?
Oh my gosh.
Oh, it's a lot of work.
No. I
It's-
just looked at all the. I'm sorry, but I just looked at all the grades as to how you guys all did. And it's just
Oh, wait, is it for like 3 lectures? Or-
everything, like homework.
With the homework you get? I think I've been doing okay on the homework.
I mean, I guess you've been keeping up then, but a lot of people have been like pushing it super low.
Oh, yeah, I try to do it like right after class.
That's the best time to do it, to be honest,
Yeah.
because everything's like fresh.
Yeah, but yesterday, I don't know what I did this week. Oh, I did some other things. That's why. And I'm missing out on Wayne's to be here.
You're missing out on what?
I'm missing out on Wayne's to be
On wings,
here. Yeah, Wayne's isn't like the food.
like the chicken. I got you.
Hopefully I can finish this off. Call this one.
Mm-hmm.
Yeah. You're gonna have to like go through that hanging beam thing again, because that was.
I can go through the gymnast.
Okay. Is the disc, what's up with that one? Or you can't find it? You know
The
that?
disc and string. Yeah, I don't know why it's not popping up.
Are you trying to do this?
Oh my gosh, my computer is ridiculous right now. Let me shoot it. Interesting. Whoa, yep, that's not right. It's funny when you look at people attempting to solve the problem and they clearly don't know what they're doing. But
You can see all our attempts too.
Yeah, this instructor can
there's a lot of
see all
graphs.
everything. How many submission you had?
there are a lot of
Like,
graphs.
I
I
put in
can see.
1/4 and a half.
Okay, I can help you out for the first guy.
Okay.
For the first first problem.
Why is it 2/3? You just put in 2/3 and it worked. Why is it?
Yep. Yeah, that is the answer. But
Wait,
yeah.
why torque?
We have been talking about the torque in past 2 weeks.
I can't read my word.
I can decipher it.
Is my handwriting bad?
No, it's just that
Very.
it goes from like here to here and then all this other stuff.
Because it's the ratio between rotation and total. So you just have to.
But how do you get that? Because you have.
I'll send it over to you.
Where is
What's
it?
this?
Like, I don't know, like,
I like you. So creative.
It's just this.
No, he's gonna take it from you. He's gonna take it from you.
Can you give me one?
No.
Can't teach
I
me
ran
how to
out.
do it.
You use a tool and it cuts.
All right.
It makes a lot of dust.
Here, is it cool if I call you SpongeBob as well?
Yeah, sure.
All right. Do you want to write your work on the board?
Yeah.
Please write it as neatly as possible, though.
I'm gonna try to follow. Wait, was it that dim? It hasn't. Are you sure?
It's because these lights weren't. They used to be dimmer and flickering. Remember?
Oh yeah. Oh, that's the lights you were talking about. They fixed.
Mm-hmm.
Okay, I thought you meant they fixed that. No, it's like.
Nah. They fixed these lights, but they didn't fix that light bulb. So.
Okay, I know that.
Yeah.
So that's from just
I figures in May.
stuff. But then why does it give you that equation at the bottom
At the bottom,
where it says KE rotational over KE total? You see it in the problem?
Yeah.
Because that's what I was trying to go. I don't know. We'll see.
Hmm.
wait, how do you write that? This one?
Yep.
Is that a 2F?
Yeah. No, it's the two up. So how did you get? So he's gonna ask me, how did you get this right here?
This is just something I saw in the book yesterday.
What does that equal to? Hold on, let me keep looking. Oh wow, that's a lot.
Is that the word for the problem?
I mean, it's just like a lot of writing down, but you can simplify it to that. And then I equals mr squared, v is equal to r squared. can see if I can try. Better write this down. Physics. V equals R omega, right? Yeah. So they're just asking for the ratio between the two. What fraction of the puck's total kinetic is rotational? So they're asking for KE rotational divided by KE total. Okay. So A, cool. Okay. Rotational is 1/2 omega squared. So we have 1/4. Interesting. Can you simplify this question? Oh, V squared. Oh, yeah. Oh, you got it. One fourth. Okay, you got it. Wait a minute. I got 1/3. Why isn't that? It should be correct if the puck rotated without slipping. In this case, there's no friction, so you cannot use V equals omega R. So if you can't use V over omega R, that means this is going to have to be that. I'm so close right now. KE rotation is equal to that. Yeah. Whole.
You doing it the long way?
Whoa. Holy crap. What are you writing? Wait. What? Okay, so.
How did you think it?
Wait, so. I am so lost right now. I know how he's doing that. I mean, I can show you how I did it, but I ended up getting 1/3, but 1/3 is not correct. But the 1/3 is because I'm assuming that it's not slipping. So it's without friction, of course. Okay. Interesting. All right. Let me see if I can. Hold on. Holy Jesus. So much work. Do you understand any of it? No.
Okay, I just see a bunch of formulas. I'm like, okay, you move this around.
Okay. Let me see what I can. Okay. Well. Oh, thanks. As long as you understand what you're doing, you got the right answer. So, SpongeBob, I think you're okay. But. All right. So correct me if I'm wrong. So KE total, right, is going to equal to KE of rotational plus kinetic energy of transit, right?
That's how I started.
Right? Okay, cool. So we know that KE rotational is equal to what? 1/2 I omega squared, right?
Yep.
But we know that I is equal to what?
1/2 MR squared.
Yes, 1/2 MR squared and then omega squared, right? And then what is the translational?
Translational.
1/2 M.
Yeah.
Yes. Okay, but now what is V though? So this is where we run into problems because apparently in the thing it says that we cannot assume that we cannot use that V is equal to omega R.
Oh, I think that's what it is.
Yeah, that's the issue because if you use V equals omega R and you do everything, then you'll get 1/3.
Okay.
You should get 1/3. That's exactly what I did. But then I just read it and it says you cannot use V equals MR. Reason being is because there is, in the case that there is no friction, you cannot use V equals omega R. So do you?
Acceleration.
Acceleration times time. So, wait, so how would you put that in there? Say one
You
more
put
time.
it in for V.
Just put AT.
V equals to AT, so.
Okay, so then this would become 1/2 M AT squared. Huh. See, now my thing is, if you do that, then you need to be able to match this with this. So R, is there a formula for that? That equals V though.
Actually, when I did it, I changed omega squared to be V over R squared. And then
Wait,
kept
you,
the V's.
oh, okay. Well, I mean, you can honestly just take this and just make that V squared.
Yeah.
Right, but that's the same thing though.
Oh, well, and that's why I
Yeah,
didn't. Okay.
it's basically the same thing. Oh gosh, seriously, why? Where's the help key? Oh god. Whoa. Did you really?
I think so. And I probably forgot,
That would have been nice.
but instead I did my pre-life forget and made eggs. So it was still okay day.
Oh, that's annoying. So yeah, so you use
So this is my saw. I just
yes. I'm just reading that right now.
Oh my goodness, the BT squared.
Omega is equal to
Oh,
AT
right.
squared.
Yeah.
Okay.
no. This is alpha.
Or alpha, yeah.
This
Oh,
is-
that's alpha. I thought that was A. Just kidding. Okay.
So I use F times R equals to I alpha. So find the relation between alpha and the force because acceleration equals to.
That's how you got that. That's how you got alpha is equal to 2 L.
So they have the common vector, so it can be compared.
Yes. So how would you reduce? So then you would replace this edge, right?
Yes, replace this one. So they are in like m a squared t squared. So this one is 2, this one is half. So
Wait, this would be right. Is that what you're saying?
no, you have to plug in the alpha equals to 2a r. So times t, so the whole thing is and
Yes.
cancel and cancel.
Yes. So yeah. So this would be gone with that. Is that what you're saying? Yeah.
Yeah, and this one,
So then you're just left with 1.
this one and a
Oh my
squared and t squared.
gosh. Yeah. Okay. So here. Yes. That's exactly how you do it, actually.
M a squared t squared, and here's
It's the same thing.
yeah, it's the same thing.
So then you're
So
fine.
it's like 2,
Holy
1,
Jesus.
so
Okay. All right. Sweet. Oh my gosh. Okay, that makes sense. Did you follow? Or no? Okay. So you know that F cross R, right, is going to equal torque, which is equal to I alpha, right? Now alpha, or how do you, yeah, it's alpha, right?
yeah.
Yeah, alpha, and then just rearrange, and you know what I is equal to, is 1/2 mr squared. So the R cancels out there with that squared part, this 2 comes up here, right? And it's 1/2, and bring that up. So then you're left with this equation. Alpha is equal to 2F m over mr. And then you use this equation and rearrange it to solve for acceleration. Or yes, yes, because you know that force over mass, this guy right here,
Oh, yeah.
is equal to A. So that's why he's reduced that to A. So it's just 2A over R, which is alpha. But we know that by definition, omega squared is equal to alpha t squared. So we take alpha, plug it into here, right here, so it looks like this. So that's equal, so it goes to here. So it's 2A over R and then times T and all this quantity squared. This is all equal to omega squared, correct? So what we do is, remember that we have omega squared right there. So, I mean, you can honestly just skip this step and plug this whole thing in for omega squared, which is going to end up being, because if you just take the square, plug it in there, it's going to be, it's going to be 4A, right? This whole entire thing squared is 2 squared A squared over R squared, and then times T squared, right? So when we do that, this equation right here ends up being, if you want to look at it, is 1/4, you go mr squared, right? And then omega squared is going to be this whole thing, so it's going to be 4a squared over r squared, right? So the 4's cancel out, the r's cancel out, and you're just left with ma squared. So this is all going to equal just ma squared, right?
T squared.
Or, yeah, and there's also, shit, yeah, I forgot about this. Yeah. So this is, and also t squared. But I mean, again, I mean, if you want to write a little bit more, so you can actually see it. Yeah, right? So all of this is just for the rotational, right? So now translational, though, it's really simple. We just figured this out right here, right? So you take this, wait, was that? Yes. So this plus this guy, right? So if we take, so k e total is going to equal the 1/2, and this is at squared plus, and this is just 1, right? 1 at squared, correct? And so what does that equal to?
3 over 2.
Right? So this is 3 over 2 at squared. So yeah, so now we know what that is, but then we also know that the rotational is rotational is what we got, which was this guy, right? So we know that this is rotational. Yeah. So we do KE rotational over KE total. That's going to equal just, it's just going to be 1 at squared over this guy, which is 3 over 2, and then this quantity basically, and same thing, flip, you get 2/3.
Is this type of thing gonna be on the test?
Honestly, a lot of these questions, I mean, based off of your first exam, were the homework problems similar to the exam problems?
Yeah, but like nothing everyone gets like use this phone to like move it around stuff.
Yeah, I mean, it's just, I guess it's just good to know, because honestly, if you learn all the harder stuff, these stuff is gonna be like super simple. It's gonna be like very direct. True, that's very true. But yeah, so that's the answer here. All right.
Sent out an email. 11.
Who, me?
Yeah.
Yeah, I did. Look at me. I'm so prompt. All right, do you want to do the gymnast problem?
Sure. Like, you don't want to do the spear on the point.
I mean, I can if you want to.
Is it quicker than the gymnast one? I haven't started any of them, so.
All right, well, let's go to the ones that I can show you
All right.
without like having to go through that
Yeah.
whole entire spiel. You already know how to do the hanging beam one, right?
I can remember like the first.
Okay. All right. Well, let me go here. Gosh, this is so dark. Okay, so the gymnast, what does it look like? So we got really horrible. We got this dude there. Got a beam. You got a beam. All right, so this guy has a certain mass. The beam, it's not attached to the two supports. The beam has a mass of, so it has a certain mass and has a certain length. Yep. The beam, blah blah. Each support is 1/3 away from the end. So this is 1/3 L, 1/3 L, 1/3 L, right? Initially, the gymnast stands at the left end of the beam. So we'll denote that as 0. What is the force the left upper support exerts on the beam? Okay, so whenever you're dealing with this stuff, you can see like if this guy just stands, you can see a potential for rotation, rotational force. Cool. So we know that the summation of torques is equal to what?
Zero.
Yeah. Nice. Okay, so now we basically, you basically just go straight into it with figuring out uh, what you would call it, based off of where the guy's standing, where the beam is, and then you can figure out what the force is based off of those two values. So you could do it that way too. There are multiple ways of solving it. It just depends upon where you put your point.
Yeah.
Rotation.
Probably put it below.
You don't put it left, you put here, you put there, too.
I feel like just one of the ends is just always easier.
It's always easier, yeah. Okay, and then they say, what is the force the left support exerts on the beam? Okay. Okay, so interesting. And then M2, which is the whole entire thing. Why is it 1/6? 1/6, this is going to be a half of the 1/3. Oh, unless they're going from here. How would they do it from here? Minus the force of the left-hand side, which is 1. Interesting. Okay. All right. Well, they did it from here. Quite curious. Not 100% sure why, but they did it from there. All right. So if we do it from here, how would you solve this? So you have 3 components, right?
Yeah, you got the guy.
Yes. You got the dude. You got this thing, the support, which you're trying to solve for, and then you have the beam, right? So if we have 1, 2, and 3, what is the first guy? Based off of this, that's the rotation.
It'd be 2 times 1/3L, or 2/3L.
Mm-hmm.
Times the, oh my goodness, it says force, right?
Yes. And what is the force?
So his force would be the 9.8, or 9.8 times his weight.
Yeah, times his mass. So you got M1G, right?
Yes.
Cool. Now what's for the second one?
And then we have center of mass parallel axis there for no, we don't. I have to think. Oh, God. Hold on. So for the second one, wait, second the beam or the
Second one is this guy, the support.
okay. So then we have the support. What is the support?
Wait, what the hell did I do?
Do you not need?
No, yeah, I did that right. I did that right. So.
Does the beam not have mass? Do you have?
No, it has mass. Wait, yeah, no, that's right.
It does.
Yeah.
Okay.
Or unless you want to go straight to the beam, that's fine too. Either or.
I'm trying to figure out. Not the beam. I meant the support. Sorry. 2 supports don't have. Because it's support. The beam is supporting.
It says the beam has mass.
Does it give the mass?
Yeah.
No, not the beam. The support.
Oh, no, the support does, no, because you're trying to solve for the force.
Right.
So you can just denote it as force. instead of doing like M times G.
Okay.
So
The force times 1/3.
yeah.
Now. And then that's just it.
So you're missing one more component. If you were to do that, that would assume that the beam is massless.
Oh, times the mass of the beam.
But you need the beam. You need the momentum of the beam. No, not the momentum. Sorry, inertia.
Oh, okay. So I was right about parallel.
Mm-hmm. So then this guy, you have that mass, right? Or the force, so mg times what?
Wait, sorry, what?
Mg times what?
mg
Because if
times
this
the
is
weight of the beam.
if this is where your actual rotation is, and this is the whole beam, this is where the center point is. So it's half of 1/3.
Yeah, 1/2 times 1/3 times the mass.
Yeah.
It's radius
Yeah.
plus mass times. Oh, it's just that. It's not. Wait, it's not this other part right here. Because we did the ICM. But
The distance from the scan axis to the center of mass of the object. Yeah, let's reach for that. That's what it reduces down to.
okay.
So then you basically have to take this guy. It's going to be positive. This guy's going to be negative. Positive. Sum those all together, and then you solve for FL, which is the force of the left beam.
And basically the same thing. Or
Yeah, very similar thing for the next one on the right side of the plane. But in this case, though, you're going to be subtracting this one. So for number one, you're doing that, but for number two, it's the same thing, except this will be plus. This one's still minus, this is still minus. But then this one is minus. And then you solve for FR. Not two. Yeah. Ooh, next one's pretty cool.
So can you explain how like something else is negative, something else is positive? They're working in opposite directions, right?
Yes.
So the guy should be positive,
Mm-hmm.
it's going counterclockwise. And then being
Wait, say again?
the guy
Uh-huh.
positive because he's rotating counterclockwise.
Yeah.
And then the being or the support is working against that.
Yeah.
So it should be negative.
Yeah.
And then the beam, how do you figure out the beam? The beam is like gonna, which way would it go? Like, how do you find that one, I guess?
I was trying to solve for the left side beam.
Does that make sense, what I'm asking?
Yeah, the beam, and if you take the rotation at this point, this beam is still going to be going down. That's so basically the same thing as the person.
Okay.
Yeah. And then in the other case, though, because you're solving for this one, you're going to take your axis of rotation here. But this time, because your axis of rotation is here, the beam is going to be going up with is going to be going up instead of going down. So that's why it's going to be negative. Yeah. And then, does that answer your question?
Yeah.
So C is actually pretty interesting. It's really not too bad though. So it's asking about how much extra weight could the gymnast hold before the beam begins to tip. That's it? Okay. So this guy, person, M1, M2. So we're talking about when this guy goes down tips.
Oh, okay. Cool. So this is the part where it's just long stuff.
Hmm?
It's just long and takes a while to try and figure out. Actually, I really should. Because,
Which one? You're talking about?
no, I'm just like trying to go back to the first one. 'Cause here's the weight, and then the 2/3 was from, was the distance from the rotation.
Mhm.
And then the football, 5 was the length. The same for this one, we're trying to find this.
Yep.
We've got 1/3 times 5, because 3 times 5, 5 was the length.
Yep.
And what the third was from this. Oh, yeah, it's 1/3. Okay. It just looks weird. And then this one was 1/6 because the center of mass of the beam. Oh yeah, we do the moment of inertia, and the beam is considered a cylinder then, or is it just 1/2?
What is?
Because we had to do the inertia for the beam, right?
Yes.
So it was 1/2. And so is it considered a cylinder for the beam? Because we used 1/2 times 2 for the third, right? Yeah, 1/2 times the third
1/2 times the third. Yes.
to get the 1/6.
I guess we just. Wait, hold on. No, don't you use I guess in that case, yeah, we'll just consider it cylinder.
Okay.
I mean, when it comes to the test, you just write down. If it doesn't give you specifics, then you just write down. I'm assuming that this figure, this part of it is this.
But he'll probably get that.
They'll probably give it to you. If not, just go up to him and ask him. Yeah.
Ask who?
Professor.
Professor Dowski.
Yes. All right. Are you good?
Yeah, for number 1 and 2, yes.
Cool. All right, number 3 is asking how much extra weight could the gymnast hold before the beam begins to tip? So it's kind of like the same idea when you go back to the force thing. It was like how much force is required until like something begins moving.
We have to set it equal to like some other thing.
Right, like with like the kinetic and static and kinetic friction there. But basically you're just trying to figure out when it's going to tip. So basically at any point, so you know that the torque, some of the torques have to equal 0, correct? Right? And in this case, the supports don't necessarily matter, but basically the supports already indicate where your axis of rotation is going to be. So in this case, would it make sense to have my axis of rotation here or here? On this guy, right? Because if it was here, the support is preventing that. So obviously here, because this guy wants to do that, and this guy wants to do that, right? Okay. So we know this is our point of axis of rotation. So you basically just go through the same steps as what we did in the first two problems. Instead of finding force, you're just solving for an extra mass that's tacked onto it.
What do you mean by extra?
So this guy is going to be, you want to solve for an extra mass. So we'll just put M because it's one M, one M2, right? And say it's like a ball, like a weight. Okay, so this is going to be the extra mass. So basically they're asking how much of this mass needs to be until this guy actually tips.
Okay, so you would leave and just keep that.
Exactly. So what is the moment of inertia?
Oh, so he's ball.
What? He's a ball. No, he's holding a ball or holding a weight. Yes. Nice. All right.
You said, like, you drew the circle, so I was like, all right, so.
I'm not. No, it's like he's holding it, dude. He's holding it. He's holding it. He's holding it right there.
All right. So then it would be his weight, but you don't know his weight, so M times 9.8 times, well, he's, I don't know what else to add,
Really close. Really close.
but like he's, from a third L.
Okay. Yeah.
Something. What am I missing?
So what's the force?
Oh, yeah,
Force is mg, right?
that's a nine. Wait, yeah,
So what's m?
we don't know.
Exactly. So
That's
Maybe
M1.
the maximum mass
and
the beam can stand.
so what is the extra part to it?
What the one?
So the dude is holding the ball.
Yeah.
So now treat the whole entire, like the addition of the extra mass is basically being placed with him.
So
So he is a part of another total mass now. So what do I need to put here? Like what is the mass?
plus like another variable,
Which would
be
be
the ball.
exactly.
But why can't you just assume? When you wrote down M1, I was considering that as like the whole thing.
Then how would you solve the mass?
That is so true.
I mean, you could, but then you have to solve for that and then subtract the dude's mass. So you can do that way too. You can, but you can't write M1 in that case because
Okay.
it's not M1, because you're given M1. Otherwise, you're going to be stuck after all the arithmetic and you're like, wait, I have all these values but no variable. Right? So, okay, that's good though. Good thing you caught that. But that's another way to solve it too. You just have to be careful with your variables. And then what else is there left?
The beam.
Okay, so what is that?
So then
Well, first of all, it's going to be plus or minus.
that's plus, but the other guy's plus 2. Both plus.
The guy's plus, the beam is going that way.
That's plus.
No.
Wait, counterclockwise?
Oh, I think of it more so like down and up. Like whatever's going down is all one uniform thing, whatever's going up is also one uniform thing. It's the opposite.
Oh,
That's how I do
okay.
it. So it's just going to be
That
minus,
okay.
right? What's going to be minus what?
So then minus 1/3 L
Okay.
from the center of mass thingy, and I think it's one of the good words. Center of mass 1/3 L times the mass of the beam, so M2.
Are you sure it's 1/3 L?
No, it's not.
It's not.
1/6.
What?
Yes. Why is it 1/6?
Oh, because the 1/2 because we're considering it a cylinder.
So 1/6 L, and then G, the force, which is M2G, right?
Yeah.
And all this is going to equal to what?
0.
Exactly.
So
Yep. Oh, what's going on? Yeah, so we got that, we got that. Yes. Solve for that. and then just solve for n values. Yeah, so this one ended up being relatively easier than the other two. The other two require a lot more formula manipulations. All right. You ready for this next one?
What's the mass of E?
Oh, it's not about the choose
118.
Yeah, you did.
The mass of Oh,
Oh, yes, sir.
what?
Oh, wait. So another question of the same. Oh, you're still. Oh, okay. I thought you meant next one. I thought you were going to like the next set of problems.
Oh, no, I'm
I was gonna
gonna
ask what at what location does the gymnast need to stand to maximize the force on the right support?
Hmm. So
So,
location is to sustain to maximize the force on the right support.
I'm gonna take a guess. Would you stand at the right support? And that's gonna be wrong, and I'm gonna ask you why.
That is wrong. Um,
That's okay.
I don't know where I answered it. It's kind of weird.
what location does gymnast need to stand to maximize the force on the right support? Okay, well, if you know that that's wrong, what's the next one?
Well, I mean, if you go all the way to the end, would it really increase? But it just,
Would it?
oh, when I saw it for the first one, and it was all the way at the left, that was a pretty big force on there.
Okay. This is where you're gonna have to think conceptually, and this is actually a super great example. Okay. So I'm actually gonna draw it. I'll just try to do it better.
Oh, well, you could have cut that.
Nah, it's chill, it's fine. So conceptually. So you have three scenarios, right? So you have this guy. I'll just denote him as a circle. So that's one.
Yep.
Right. Number two, they say where?
Right on it.
Right? So that's two.
At the right edge.
And this would be three.
Yep.
Okay. So why would it not be one?
Because that's like even.
Exactly. So the mass distribution that is going, I view it as like the mass distribution is going equally on both these supports, right? Now with this one, all of your mass is going onto this support, right? Right. This one's kind of just there, but technically this is still supporting it a little bit.
Mostly.
Mostly it's on here, yes, but a little bit is on here. The reason being is because in order for this statement to be true, that all of your weight is only being placed on support, is if
It's like
if you have that, right?
like a
Exactly. That is when it is perfectly on top of it, and that this distance has to be the same. This distance is not the same as this distance, right? So therefore, this is still holding some type of support, right? Okay. So you want to maximize in the sense that you don't want basically in order to maximize the amount of weight that's going on this support, you need to make sure that this is not going to be supporting anything at all. So when you look at this one, all of your mass is going here. This wants to go up, therefore this won't matter anymore. So all of your force is going to be in here. Remember last time the example that he gave us during class?
With the ruler.
Yeah, like when you're holding it like this. Oops. Okay.
Exam
When we're holding it like this.
yesterday? Don't you like that? I would put it.
But like, remember last time, so basically you held a rod. Think about just like, if you're just visualizing this, or thinking like you're actually doing it. You're holding a rod out like this. If I place a mass on top of my hand at your pivot point, and which your hand is at, you can rotate this freely, right?
Yeah.
Super easily. But if I place the mass further away on the
Oh,
board,
yeah,
you have to really
Yeah.
pull up really hard on that. So that's when all the force is going to be exerted at this pivot, at that support. Make sense now? Cool. Sweet. All right. We only have like 5 minutes left, actually.
That's fine. I think I'll be able to get through it.
No, we can still finish it up. Though. We can probably do one of the problems.
We can do this all night long if you want. Eat what?
Plus, I have a camera. Actually, I don't really need to go to it, but
How many people go to
it's
that?
kind of just like more than this one, I think.
I would
Actually,
not doubt that.
yes, because there's a physics review like right before it with a different SI, and some people from that section just stay because they're also because they're Vietnamese,
I see.
so they just stay.
That's chill.
I'm usually like the only guy who comes in, but they're already here. The guy's pretty cool. He's a chemistry major and he's a co-terminal too, I think.
Chemistry major co-term. Wait, his name Andy?
Yeah, Andrew.
Andrew Shahidapur?
Yeah.
He's my roommate.
What?
Mhm.
Oh.
Yeah, we both do SI.
Oh, wow.
Except I did SI first. I did chemistry first. Just saying. Just saying. I was gonna do chemistry because that's what I've been doing all this like every year, but I had to switch to physics because the chemistry slots didn't work with my like the class itself. It didn't work with my schedule, so I wasn't able to like attend those lectures. So therefore, I can't do that section. But so physics is a little change of pace, but it's all right.
Yeah. Well, I'll be seeing him. That is he? He's a 4th year.
Mhm.
Oh, he's 3rd.
Yeah, he's like he should be 3rd year. Should be, yeah.
Oh.
Yeah, he's not 4th year. I mean, maybe he says he is. I don't know.
I thought credit standing.
Credit standing, I'm pretty sure he's still 3rd year because he's staying here for co-term for an extra full year. So yeah, I guess I'd consider myself a 4th year credit wise because I'm leaving here after 4.5 years with co-term. So like, I mean, I guess kind of. I still consider myself
That's weird
3rd
though.
year.
Is he leaving winter? He done?
Yeah, and then I have a whole entire spring just doing nothing. Or most likely I'll be like doing some type of internship or whatever, or try to do some research or jobs, get some money.
Yeah.
You know,
Exactly.
anything. I did get a random email from a recruiter and was like, "Yo, you should apply for this because we kind of want you." So I was like,
Wow, that's nice.
It's interesting because you know what it's for? It's for a company that rallies up like all the. It's kind of like how to describe it. This is very loose connection, but kind of like a Walmart where Walmart kind of has like a whole bunch of different brands in one area, right? So this dude is called like Amer Sports or something like that, and it takes like all these different tennis companies and wraps it up into one. And I have like years upon years and years and years of experience with tennis, like tournaments and coaching and all that good stuff. And then they're asked me to apply for a position that combines not only like the enthusiasm of like tennis, but the engineering and research behind it. And I was just like, yo, I see why y'all want me now.
How did they find you?
I don't know. They emailed me and was just like, hey, so we found your resume on Indeed or like on LinkedIn. Was it Indeed or?
I gotta make one.
Yeah. Yo. Well, I mean, you are first year, so I mean it's okay. But if you're like really prominent on trying to find internship after your first year, then making a LinkedIn would definitely be your best bet.
So then I gotta like look and see how to do a resume, and I don't have much stuff.
Go to the career. Okay, I suggest going to the career.
I've been there.
But I've.
Once.
You have one more than I have. So
I got the little handy book. They're like,
that's such a like. Here, read it, and come back when you're done reading it, which not many people do read it. So it's like, well, anyway, sorry, I'm cutting into your time. It is 6:30. Do you still want me to go over?
It's all good.
You sure?
I do have problems. I got older guys.
Sounds.
I didn't know what that means.
And then he's gonna ask what it is to mess with someone.
Are you a bother?